Hi students. In this lecture, I am going to discuss problems. Let us see first one. The acceleration A of the Planck P required to keep the center C of a cylinder in a fixed position during the motion is. So condition is that no slipping takes place between the cylinder and Planck. Okay. Let us see how to start. Right. First, make the given diagram. So it is inclined plane. On that, having one Planck. So a Planck is there, which has acceleration A. So this is now Planck. And this has acceleration A. Now on that Planck, there is one cylinder. This is now one cylinder. So now given condition is that center of the cylinder does not move. Okay. Condition is given that center of the cylinder does not move. See once acceleration A of the Planck required to keep the center C of the cylinder in a fixed position. Okay. And one more condition is no slipping takes place between the cylinder and Planck. No slipping. So we have to find acceleration A, right? Let us see how we are starting it. So first condition is center of the cylinder is not moving. That means acceleration of center of mass of the cylinder is 0. So that implies net force on the cylinder is 0, right? I am repeating. Acceleration of center of mass of the cylinder is 0. Its meaning is net force acting on cylinder is 0, right? So first focus free body diagram for cylinder. You can focus its weight component acts down the incline. So its weight component is mg sin theta. This has a contact with the Planck. So by the Planck on the cylinder, frictional force must be up the incline. And condition given that there is no slipping. That means the friction must be static. It is Fs. So since the center of mass of the cylinder is 0, means acceleration 0, we can write Fs is balancing mg sin theta. So first condition, frictional force on the cylinder is balancing mg sin theta, right? So now we have to calculate acceleration of the Planck. See how to get it. So we are given a condition that is no slipping. Okay. No slipping means for the contact point of the cylinder, acceleration must be same as that of the Planck because there is no slipping. In fact, we are saying velocities are equal. If we differentiate once, we get accelerations. Okay. So you can see here acceleration of the bottommost point for the cylinder must be equal to A. Okay. Since center of mass has no acceleration, now only possibility is there must be acceleration because of rotation. Okay. Because of rotation, this bottommost point is having acceleration. That is now R into alpha. Okay. That means first focus now torque. Say torque on cylinder, torque equation about center of mass. Then because of gravity, because of normal reaction, no torque. Torque is only because of friction. So torque on the cylinder is only because of friction. So we are taking torque about center of mass. Okay. It is Fs into R. That is mg sine theta into R. This is equal to I into alpha. And I value mr square by 2 into alpha. Then see what we get here. R gets cancelled. Alpha equal to 2g sine theta upon R. Okay. That is now alpha. Now for contact point, acceleration is only because of rotation. Therefore, A must be equal to R into alpha. So R alpha is equal to 2g sine theta. Okay. So key point is that here center of mass of the cylinder has no acceleration. Means no translation. It is now only rotation. So here no slipping. That's why it's a tangential acceleration. Its tangential acceleration is equal to A. So here we should not say acceleration of the contact point is equal to A. Okay, that is not a correct one because due to rotation, this contact point is following now circular path. And because of circular path, what happens is for acceleration, it is having two components, tangential and centripetal. That's why acceleration of contact point is not equal to acceleration of the plane. So we have to say that tangential acceleration of the contact point is equal to acceleration of the plane. That is what we have done here. Okay. Let us see next one. Right. See the question given. A uniform rod of mass m and length L is held horizontally by two vertical strings of negligible mass as shown. Immediately after the right string is cut, what is the angular acceleration of the rod and also determine the tension in the left string. So we have to find angular acceleration of the rod and also tension in the left string. Let us see. So given a uniform rod which is connected by strings. Strings are vertical. Now condition is that right string is cut. So when right string is cut, just after cutting, what is the tension in the left string? Okay. Let us see how we are solving it. Suppose in the left string, tension is now. So take it as T just after cutting. And here weight mg passing through center of the rod downwards. Let us focus now force equation for center of mass. Okay. Center of mass force equation means, if you see carefully, center of mass follows settler path. It follows settler path. Then these two are becoming along the tangent. Okay. So writing here tangential force. It is mg minus t. This is now tangential force, which is equal to mass into tangential acceleration. That is 8. And 80 means it is r into alpha. Here r means L by 2, right? So L by 2 alpha. So to know tension, we require alpha. And to calculate alpha, we have to calculate torque. Okay. Now see torque equation. So we have taken force equation for center of mass. Now torque equation about center of mass. So about center of mass means because of gravity, no torque. Now torque is only because of tension. Okay. It is now T into L by 2. That is equal to I into alpha. And I value. Torque is about center of the rod. It is ml square by 12 into alpha. Now see L gets cancelled and 2 here 6 times. From this alpha value 60 upon ml. Okay. Substitute this now in this equation. It is mg minus t. Or say what is this value? L by 2 alpha value how much? L by 2 alpha. L by 2 alpha 60 by m L. Okay. And I'm taking here m. Take m here. M L gets cancelled. 2 here 3 times. This is now 3t. Okay. That means 3t plus t 14. So t value mg upon 4. So it is a very simple and direct one. Okay. Let us see next one. Right. Let's see the question given. A uniform rod of mass m, length L, is suspended by two wires P and Q. Okay. P and Q, two wires. The wire at Q suddenly breaks. Find the tension T in the wire at P immediately after the wire at Q is broken. Okay. So in the previous problem, strings were vertical. Okay. So here strings are not vertical. See what we can do here. He's asking just after string is broken. Okay. Right. First make the diagram. Left string is, sorry, right string is cut. So this is now uniform rod. It is connected to two strings. Right string is cut, left string is there. Suppose tension is now T, which we have to calculate. Okay. Now see free body diagram. Here mg vertically downwards, mg. Now tension, we can take two components. Let us take left as x-axis and down as y-axis. So for tension, one component that is left and vertically up. See, given angle is now 30. So it becomes now, this is now 30. So this is a t cos 30. And this is a t sin 30. Now focus. See here, key point to start the problem is along the string length, there is no acceleration. Relation is that just after cutting, that means for this point, there is no omega. Since there is no omega, there is no centripetal acceleration because centripetal acceleration is r omega square, right? So since it is just after cutting, there is no omega. That's why there is no centripetal acceleration. So along the string length, acceleration must be zero. Okay, let us focus now. First, focus a force equation for center of mass. Coming to center of mass, along x-axis, we have tension component that is T cos 30. So writing force equation along x-axis. So T cos 30 that is equal to m into ax. Okay. So from this, we are going to get the value of ax in terms of tension, which we have to calculate. It is T cos 30 root 3 by 2. So root 3 by 2 into T by m. That is now x component of acceleration of center of mass. Right? Next, coming to along y-axis, it is mg minus t sin 30, that is t by 2. That is equal to m into ay. Okay. So from this ay, that is equal to ay is equal to g minus t by 2m. Okay. Next. Now focus torque equation about center of mass. Okay. About center of mass, because of gravity, there is no torque. Now torque is only because of tension. Okay. And we can see because of T cos 30, because of this component, there is no torque because this is a passing through this point. So now torque is only because of this T sin 30. Okay. So writing torque equation about center of mass, that is T sin 30 into L by 2. That is equal to I into alpha. And we are taking torque about center of the rod. About that axis, I value ml square by 12 into alpha, right? So from this, what is the value of alpha? This is 6 times alpha equal to, this is tension 1 by 2. So it cancels here. So alpha equal to 3t upon ml. Okay. Right. Now coming to here. For this point, along the string length, there is no acceleration. So I'm making diagram once again here. For this point, along the string length, there is no acceleration. That means now we have take acceleration equal to 0 along string length. Now see what we can do here. This is ay, right? And this is ax. So we got ay. It is downwards, ax left side. And you can see because of rotation for this one, acceleration is there. Rotation is now like this. It is a clockwise. So it is now r alpha. It is r alpha. R means L by 2. L by 2 alpha. That is vertically upwards. Okay. Now take components for this along the length of the string and make it equal to 0. So this is right now taking components here. AX, this is 30. So this is now AX, AX cos 30, AY, that is downwards. Now this angle is, it is 60. So it is now AY cos 60. R alpha, that is upwards, right? R alpha is upwards. So this is 60 means this also 60. So L by 2 alpha cos 60. So I'm writing here L by 2 alpha cos 60 plus AX cos 30 should balance AY cos 60. AY cos 60, right? Now see what we get here. Substitute values in this. It is L by 2 in the place of alpha 3t by ml into cos 60 1 by 2 plus AX. AX value is how much we got? AX root 3 by 2 into t by m into cos 30. I'm making calculation only. Root 3 by 2 into t by m into cos 30. Root 3 by 2. It is 3 by 4. 3 by 4 t by m. Okay. That is equal to ay g minus t by 2m into 1 by 2. Or I can say, okay, 1 by 2 here. Now see what we can do throughout. 1 by 2. Here 2 gets cancelled and here 2 gets cancelled. Next, see what else we can do. Now simplify this part, okay? So here L and L cancelled, right? Remaining part is now 3t by 2. 3t by 2. This also 3t by 2. That is now 3t, right? 3t by 2. Sorry. Yeah, 3t by 2. 3t by 2. 3t by 2m. And here it is now t by 2m plus t by 2m. That is equal to, see what else left here. It is only g, right? Cross check one, the calculation, what we have done. 3t, 3 by 2 plus 1 by 2 is 2, right? So 2t by m. So t equal to, but I think here calculation something went wrong. Cross check once. L by 2 alpha value 3t by ml. Okay. cos 60. It is 1 by 2, right? Plus AX. AX value, it is now root 3 by 2 into T by M into cos 30, root 3 by 2. It is now 3 by 4. So 3 by 4 T by M. Next, G minus, wait, here, G minus T by 2M into 1 by 2. Okay. So here 2 and here 2, 3 by 2, 3 by 2. This is 3. Okay. This is a mistake I done here. Right. So it is now 3 by 2, 3 by 2. That is a 3. 3 plus 3 by 2. Okay. 6 plus 1, 7. 7 by 2. It is now 7 by 2. T by M equal to G. So that implies tension is equal to 2mg upon 7. Okay. So here key point is that along the spring length, there is no acceleration. The reason is that just after cutting, for this point, there is no omega. Since there is no omega, there is no centripetal acceleration. That's why along the spring length, acceleration is 0, right?